Okay, this question is starting to get a little bit more sophisticated in our acid-base considerations. We are essentially still figuring out which one is the stronger acid, but now we're asking the question in a slightly different way. Ultimately, in organic chemistry, we're very much interested in chemical reactions. And so what we need to do is use our knowledge of acid strength to predict the favorability of a reaction as far as an equilibrium is concerned. Most reactions can be described as equilibriums to some degree, and we want to know if the products or the reactants are favored in an equilibrium reaction. And knowing relative acid strength is one way to do that. So what we have here is a system, an acid-base reaction, where as written, it looks like the negatively charged sulfur grabs the proton off the oxygen, or the other way to think about it in the Bronsted-Lowry definition is that the acidic hydrogen on the oxygen is donated to the sulfur. Either way you look at it, it's still the net effect is the same, but what we want to figure out is this reaction product favored or is it reactant favored? That's what we need to know. And so there's a way to think about it. We can think about it this way. We can think about it in terms of the relative stabilities of the conjugate bases. The reaction will favor the most stable conjugate base. Another way to think about it, and it really is the same way to think about it, it's just saying it in different terms, is we say that the reaction favors the side with the weaker acid. It really is the same thing because the weaker acid will have the more stable conjugate base along with it. So either way you think about it is fine. Now, when we think about the relative strengths of acids, we usually think about the atoms that they're connected to, whether or not there's any resonance, then inductive effects and orbital effects. In this case, they're all sp3 hybridized orbitals, so that's not the issue. There's going to be some resonance in all of them here. I can show you real quick. We've got some resonance, and you'll have the exact same resonance in this one as well. So resonance isn't the issue. It really is the atom that the hydrogens are connected to. In this case, the conjugate acid is, the atom is sulfur. In this case, the conjugate acid atom is an oxygen. Now, this is a little bit more sophisticated of a consideration when it comes to atom. Usually we think about the electronegativity. We generally say the more electronegative an atom is, the better it is going to be at stabilizing a negative charge. But there's really other considerations to make, and that's really polarizability. Electronegativity only works when we're talking about atoms that are on the same row. But sulfur and oxygen aren't on the same row. They're on different rows. They're in different periods of the periodic table. So we can't really just say electronegativity. We have to think about which one is more polarizable, because polarizability means more stability. It's more stability for the negative charge. Well, what makes an atom more polarizable? If you think back to our previous chapter, we thought about intermolecular forces and physical properties, and we decided that a larger molecule has more polarizability than a smaller molecule, and that would lead to larger instantaneous dipole moments. Well, the same idea applies here. A larger atom will be more polarizable than a smaller atom, and therefore the negative charge on that larger atom will be more stable. And so in this case, we have sulfur, and sulfur is larger than oxygen. Because sulfur is larger than oxygen, it's more polarizable. And what that means is that it's more stable. And that's more stable as an anion. So it's more stable as an anion than an oxygen anion because it's larger and more polarizable. So what does that mean? This one is more stable than this one. So A is more stable than B. So what does that mean? That means that conjugate acid A is more stable, is a stronger acid than conjugate acid B. And so let's go back to the two ways that we can think about it. The equilibrium favors the side of the reaction with the more stable conjugate base. That's this one. And we also can think about it in terms of the equilibrium favors the side of the reaction that has the weaker acid. And so we decided that the stronger acid is the sulfur-based acid, and so this is the weaker acid. And so we're going to get the same consideration either way we look at it. So the equilibrium favors the reactants in this case.